Hi, thank you everyone. So as Dr. Himmelfarb introduced, I'll be talking about membranes for portable dialysis, specifically separating urea and glucose for dialysate regeneration. And my co-authors here are Rambang Tang and Dr. Ratner. Um, yeah, so some background, I'm sure I don't have to go into this very much, but CKD, as per a few years ago, affects 15% of US adults and around 9% worldwide. Here I've put a map of the incidence rate for ESRD, which is a final stage of CKD. And here are just some more stats. 750,000 people have ESRD, and that requires direct medical intervention. And here, the topic here is dialysis. So as Dr. Hines introduced, the issue with portable dialysis, like the main challenge, is that so much dialysate is needed. 120 liters of dialysate is needed just per one session, which makes it extremely difficult to miniaturize into a portable dialysis system. So the solution is a dialysate recycling system, and we just saw the photoelectrochemical oxidation of urea. The problem again is that glucose is thermodynamically favored for decomposition, and that is energy inefficient and can also generate toxic byproducts. So we really want to find a way to separate out the urea and the glucose so that we can then kind of feed it into this photo-oxidation system. And here is where the membrane would come in. On this slide is a portable dialyzer schematic. So the urea removal step would be accomplished with the photo-oxidation system. And below that would be the selective membrane that we successfully engineered in this project. So some key design criteria we need are that the membrane needs to filter a minimum of 240 millimoles or 14 grams or 15, I guess, of urea in less than 8 hours. And that is just the daily molar production of urea to be excreted. And the second is that we need a high urea to glucose permeability ratio through the membrane, and that needs to be greater than 20. The third is that we need at most a square meter of membrane so that it's practical and that we can use it in a portable system. And the last two are that, of course, we need it to be replicable and we need it to be chemically inert to some degree. So the method we chose is something called phase immersion precipitation, which I'm sure a lot of people are familiar with. Just a brief overview of this technique. A casting solution is created with polymer, solvent, and also additives, which are optional. Once that solution is homogeneous, we then cast it onto a solid support, which is often glass. And this is done using a blade, generally just in a lab setting. And this casted solution is at a specific thickness, generally on the order of several hundred microns. After being casted, the solid support with the casted membrane is dropped into a non-solvent bath, which in this case is actually water. And then after which a non-solvent and solvent exchange happens, which generates a membrane matrix that is porous and which will enable the selectivity of the membrane. So after this step, we were investigating how we might improve the selectivity of the membrane, and we actually found, I'll discuss later on, but we found that heat treatment was extremely effective at improving the selectivity. And in order to kind of quantify this, we tested this in the membranes in a Fran cell, where the top chamber would be kind of a pseudo spent dialysate, and the bottom was just a solution of like a salt solution. So based on that procedure, these are some of the many tunable membranes. I'll only be talking about some of these in my presentation, but as you can see, there are a ton of things you can kind of change around just within phase immersion, this method. Here is a design of experiment table with factors and levels. And these are just some of the things that we tested. And I'll be focusing mostly on slide temperature. So the slide temperature just refers to the solid support that the membrane is cast onto. And I'll also be talking about the bath temperature and the heat treatment temperature. So our first question was, what polymer do we even use? There are so many available out there. I put on this slide 2 examples. One of them is polysulfone, which we started out with, and the second plot is cellulose acetate. And most of the polymers we tested behaved somewhat like this polysulfone membrane, where we tried to improve the selectivity with heat treatment, but it didn't really work. The permeation ratio was very poor. But with cellulose acetate, we found that not only was the permeation ratio just generally better than polysulfone, once we heat treated the membrane at 80 degrees Celsius in a water bath, we were able to push the ratio up to almost 30. So here we tested the mass permeated through the membrane by measuring the concentrations of the solutions at various time points. And over here, we were just mostly looking at the effect of heat treatment and how effective it really was at preventing glucose from passing through, but allowing urea to still pass through. And this is challenging because they're so similar in molecular weight. Urea is 60 Daltons and glucose is 180, and in the grand scheme of things, that's a very small difference. But we found that with otherwise identical conditions, heat treatment was able to completely get rid of the glucose permeation through the membrane. So our next question was that, so heat treatment works in removing glucose permeation, but it also, makes it harder for urea to pass through. So how can we simultaneously make sure that glucose does not get through, but make sure that urea is able to pass through as well? So here we looked at various temperatures. I've put 75 degrees and 65 degrees for the heat treatment temperature. And then we're able to kind of improve incrementally the permeation of urea through the membrane. And this figure essentially summarizes that. You can see that the urea permeability increases proportionally with the heat treatment temperature, which is expected, and that at a temperature of less than 75 degrees Celsius, we are able to achieve that 14 grams of urea permeation in less than 8 hours if we assume that the membrane area is 1 meter squared. So going through the conclusions, we know that based on these experiments that cellulose acetate polymer base allows for kind of a more tunable pore sizes in the 60 to 180 Dalton range. We know that the combination of a 0 degree casting temperature, which is essentially just a slide temperature and a bath temperature, along with the heat treatment between 65 and 75 degrees, is able to create a more selective membrane. So that means that the pore sizes are very tight and in the range that we want them to be. So this research is still kind of in its beginning stages, and so there's some more experiments that we hope to run in the future, and some of these include rerunning a lot of these experiments with spent dialysate from patients in clinical settings. Something else we'd like to do is to get a rejection curve so that we actually know exactly what the molecular cutoff weight is for this membrane that we've developed. And the last one is to convert these flat membranes into hollow fibers, which are actually, they're more practical and feasible to be used in like traditional hemodialysis. And here are some of the acknowledgements. Thank you to the CDI, Northwest Kidney Center, Buddy Ratner Biomaterials Group, and also the Levinson Emerging Scholars Program for funding some of my research. Thank you.